All right.
So, here's the thing I need. Let's look at this picture again. I know. You guys are psyched about this picture. It's okay. Hold your applause for a minute. Let's see. So, what do we know about this picture?
Null space, row space,
Column space
column
and
space,
another null space.
Yeah.
and a
A
90-degree
transpose.
angle, super clutch.
Row space, null space. Yes.
Yes.
Another null
Perpendicular.
space. I think so, yeah.
Dot in the middle is
Zero.
Zero
the
vector.
zero vector. On this side, I have
Null space of A transpose.
Yeah.
the null space of A transpose.
Column picture,
Let's see.
which is, or yeah, column space
The column
Space.
space.
of A, which is the same dimensions as the
No,
column,
it,
the row
it
space
is, it
of A.
is the row space of A
No.
transpose.
Oh, yes, it is the
Yeah.
row space of A transpose.
Transpose.
It is the same size
Size.
as the row space of A,
Yeah.
right?
Yeah.
That's where
So,
you're at.
here is the Here is the part of the picture for today, which is when you push on this thing, right? Using my map A, right? So I'm going to go like this. I want to be just a little bit more specific than like this stuff go over there, right? So let's get to where does this stuff go over there? So where does the null space go when you do A to it?
Zero vector.
Good. It all goes to the zero vector, the whole thing. So this whole thing gets mapped directly to the zero vector there. Okay. What is your guess about where the other stuff goes?
Well,
To the column space.
yeah, not
Yeah.
column.
It seems really obvious. Like, I know that the whole thing goes to the column space. Why do I know the whole thing goes to the column space?
Because the column space is kind of the entire matrix. Any multiple of the columns is what the matrix can do.
Good, because I look at the column multiplication picture, and the column multiplication picture says the only things you can get out of the matrix are linear combinations of the columns, right? So I know that the column space is an alias for the range of A. That's a funny equal sign. You guys with me on this?
Yes.
So, my claim today is that the row space maps directly onto the column space in a one-to-one fashion. Keep in mind that vectors in this, what is this space?
The domain.
Yeah, good. This is the domain. So keep in mind that vectors in the domain may actually look like this. This is a valid vector in the domain. It is composed of two pieces. It is composed of a piece in the row space and a piece in the null space.
Oh.
Yeah.
You guys see that? How do I know that's true?
Like,
Is it geometry?
yeah, like other than
Yeah,
the
it's
drawing,
actually because of the geometry of the space, right? So I know these two spaces are perpendicular to one another, right? And so if I'm thinking about a vector out somewhere, it could be taking a vector in the row space and adding a vector in the null space. And because those two things are perpendicular, and because they're the right sizes, right? They have to make up the entire domain. So I can write anything in the domain, and this is where I need to look at the cover of the book quick. So I'm going to call this green vector here, I'm going to call that x. And I'm going to call the other two y in the row space and z in the null space. I'm just copying the notation off the front of the book so it matches. If I had to think about this personally, instead of writing x is y plus z, personally, I'd be writing x is x row plus x null. Does that make sense? Like, I don't care about this notation. You can kind of pick either one. I'm going to draw it the way the book does, just so we can have that symmetry match. So, my question is, when I do a to this vector x, so a done to x, right, is going to be a done to y plus z,
Which is A done to Y and A done to Z.
which is a done to y plus a done to z. How do you know that? Because it's a linear operator. Okay. Now where does az go?
0.
Az goes to 0.
And that's going to go to the column space, AY.
Yet ay is necessarily in the column space because the column space is the range.
Yes.
You guys see that? Now, the thing I'm claiming is just a little bit more than that.
Okay.
The thing I'm going to claim is that I could think about inverting from the column space to just the row space. In order to make that claim about inverting, I need to know that it's 1 to 1. You guys with me on that? So my claim is going to be that A is 1 to 1 on the row space of A.
Are you cutting that from the video?
That is a fantastic noise. I thought that was a ringtone. Is it a whistle? Cool. Alright, so. Everybody with me on what we're trying to show?
Not anymore.
Not anymore. Okay, so we're trying to show that vectors in the row space necessarily are 1 to 1 into the column space. You guys see that? So my function takes vectors in the row space in a 1 to 1 fashion into the column space. Now I know that in general my function A isn't 1 to 1.
Yeah.
You guys recognize that?
Yeah.
Yeah, because there's a null component. Like, it probably smashes some stuff. If you pull a linear operator out of the world, well, if you pull a linear operator out of the world, it's probably invertible. But if you pull a linear operator out of your textbook, the odds of it being invertible are pretty low. If it's not square, it's definitely not invertible. You guys see that? So, how do I show that something's 1 to 1?
You draw the bubbles.
Yeah, I kind of draw little bubbles,
Yeah.
right? So normally when I'm trying to show that something's 1 to 1, I'm thinking about function, and I'm like, bubble, bubble, thing, right? So the situation I'm trying to avoid, right? And I'm drawing things flat today because we're in linear algebra land, right? Not in regular algebra land where I draw bubbles. Flat thing. This is going to represent to me the row space of it. Right? And over here on the other side, I've got the column space. You guys see that? I know that if I apply A to the row space, I definitely end up in the column space. You guys see that? Okay, so my concern about one-to-oneness is maybe there are two vectors, x row and x row, I don't know, x row 1 and x row 2, right? That both go to the same place. I'm going to call that vector B, I guess, because that's my kind of usual for things on the range side. You guys with me? So my claim is that if this is the case, right, if both x row 1 and x row 2 both go to B, that these must actually be the same thing. You guys see that? So I'm going to suppose that there's two that go to the same place. So suppose A x row 1 is B is A x row 2. You guys all with me? Okay. Now I'm going to do something tricksy. Anybody guess the tricksy thing I'm going to do? Yeah. So the tricksy thing I'm going to do is I'm going to actually write this as x row 2 down here equals b. And then I'm going to subtract these two equations from each other. You guys see that? So if I subtract these two equations, on the left-hand side, I'm going to end up with a x row 1 minus a x row 2. You guys see that? That's going to equal what? Yeah, b minus b is the 0 vector. Okay, cool. Then what?
So then linearity a of x row 1 minus.
Yeah, so apply linearity to this situation, right? And otherwise, you could think about it as the extremely bizarre factor an a out.
Yeah.
No way.
Yeah,
Crazy.
like that's what linearity means, is that you can factor matrices. I don't usually phrase it that way because I want you to think about the damn thing as a function. But if you catch other people talking, sometimes they'll just say factor it out. So I'm gonna exploit linearity, right? So I'm gonna say this whole situation implies that a x row 1, sorry, a done to x row 1 minus x row 2 is the 0 vector. Is that good enough? Am I done?
Either a is the 0 matrix or x row 1.
Yeah. That's exactly, thank you for falling into my trap.
Oh no.
My very cleverly laid pit trap.
It's a trap.
Yeah. Why was that a trap? What are you trying to use?
Well, I was going to say like either that or those guys are the same thing.
Yeah, so you're kind of inclined to say either A is the 0 matrix or this stuff is 0, right?
Yeah.
Yeah? Problem? That's
That's right.
trying to use the 0 product
Yeah,
rule in
the zero
matrix
product
land, and that's not a thing.
That's true. Okay, so either
No. Don't do either.
alright,
This is easier than either.
a is not invertible.
Well,
No.
wouldn't this suggest that x row 1 minus x row 2 has to be equal to 0 vector?
No, because that's
No.
the product rule stuff again.
But it does tell me that. So the trouble is, I don't know anything about this stuff because I don't know whether the matrix A is invertible.
Yeah.
And in fact, this is only interesting when the matrix A isn't invertible, right? So I have to kind of assume that the matrix isn't invertible. So if it's not invertible, what can I say about the vector x row 1 minus x row 2?
It is a vector that maps A to 0.
Good. It is a vector that A maps to 0. What does that mean?
That means that it is
It's in the null
linearly
space.
dependent.
Good. It's in the null space. So that's in the null space, right? Okay. What do you know about the null space and the row space?
They are
The only place that
perpendicular.
intersect is
They are
the 0.
perpendicular. The only place they intersect is the 0 vector. You guys see that? So this vector has to be perpendicular to the row space,
But that's where it started.
and the only thing, I have two vectors in the row space, right? So their sum, or in this case their difference, right, is a linear combination of two things in a subspace. This also has to be in the row space. You see that? Like, I've got my two vectors in the row space, right? They look like this. If I take this one minus that one, right,
It still has to be
I
in
get this vector, but it's in the row space. You see that? So this is a vector that is both in the null space and in the row space.
And the only vector.
And the only vector in the null space and the row space, because they're perpendicular, is the 0 vector. You guys see that? So this implies that x row 1 is x row 2. Because their difference is the 0 vector.
That looks like a 1.
That's so cool.
Yeah, this is super cool. So what this means, right, is that if I want to know what the matrix kind of does as a whole, right, I don't need to consider doing it to every vector. I could actually just consider doing it to rows and their linear combinations. You guys cool with this?
Yeah, that's awesome.
That's sick.
Yeah, this is kind of a neat thing. Because this means there's a decomposition that I can make that's useful. So, a vector in the domain space, I can always realize it as a vector in the row space plus a vector in the null space, and the vector in the row space is the only thing I have to push forward with A to find out where that vector went. Cool with that?
Yeah.
We're gonna exploit that a little bit.